Harvard's just cranking up the AC.
Yeah, let's crank it up the AC. Hey, Dave. Looks like it's all set up. So they, no, I know. Usually we're facing each other. In case if you feel crowded back there are a couple seats up here that are a little bit airier and
Near the fan.
you got a fan to help you out.
You look at that screen right now. Yeah, I was expecting.
The middle screen is the same.
Yeah, this is
You want to use the lens one? No, then you can do the plastic. That's probably more robust. You got the.
Like an usher in theater.
So we still started at that time. Go function.
Just let me know if you want me to shut the door. Right now, we can open because it's kind of hot, but if it gets that you can't hear it, I'll shut it. There's a mic right here.
Oh, we have a mic actually attached to the.
So is that what you
You can sit over here.
No, I was just checking about the mic.
Oh, yeah, the mic.
It's directional, yeah. And so, and they'll hear you. So hopefully everything will be good.
I'm brought to my class, so I just always say, provide you. So what do you need?
Whenever I get back to the hotel.
So maybe not for us. So then they know that. Maybe just simply the we'll work with you. Yeah, hopefully. Not like that. I saw you.
Sorry, I missed that.
Yeah, what was it? I'm doing very good.
Somebody told me you retired.
No, no. I'm doing that. But it's.
You get my TNT cup.
You know the name.
Open the data.
You didn't have a small bottle, so.
Otherwise, it'd be hot.
It's bigger, right?
Because right now we're just teaching.
So why can't we just make the students sit in front of the screen and have them by direct connection? It doesn't work.
Oh, you mean forcing the students to sit in the front?
No, how come you can't just plug the student into the computer and have direct energy transfer?
Oh, yeah. I'm afraid the impedance coupling would be rather severe.
So what's the official start time for our talk here?
Right now, actually, and Jen's gonna introduce you.
Okay, very good.
Why don't we start?
Yes, start earlier.
No, we're not starting earlier.
Oh, it's 1:55 or so. 1:45. No,
45.
1:45?
Yeah.
I always got confused.
Don't
Okay,
worry.
sorry.
So I think all these things started.
I'll get started. Today is a great pleasure to have Dr. John Mather to be here, give us a colloquium. Of course, last I gave a wonderful public talk. I assume many of you attended that wonderful talk already. Dr. John Mather really have a distinguished record, so I'm probably not able to talk about everything. But as usually a colloquial speaker, I always have to give the brief highlights of what he done in the past. First of all, PhD, of course, in physics from University of UC Berkeley in 1974. And then he had 2 years short postdoc at the university as a NRC post fellow. And after that, he joined Goddard and never left. And of course, the most important thing I want to highlight is he prize, of course, 2006, as everybody know. And he also went to join the National Academy member in 1997 and the National Academy of Science and Arts in 1998. I see the many young people here. I want to share one story about John. It's really wonderful. It's about he actually during the PhD time actually failed twice about this doing the cosmic background radiations, right? From the high mountain and failed, and then go to the balloon, failed, but he never give up. And as a postdoc, this idea doing this called, cosmic background exploration ideas, and that eventually led to the satellite, and that led to the wonderful discovery of the universe, background radiations. So this I want is we're talking about this, young people. This is how the greatest scientists, how they accomplished. Never give up. Try some wonderful ideas and try and again until now. Of course, now John is leading the JWST. This is the best observatory in the history. So let John to introduce your talk.
All right. Well, thank you, John. I would like to confess that I'm not as determined as it sounds. Because after my thesis project didn't work, I thought, I'm going to go do something else. I'm not going to work on cosmic background radiation. This is way too hard for a young person to work on. And so I'm going to go become a radio astronomer. So I got a job with Pat Thaddeus at it's at Columbia University, but it was a NASA laboratory in New York City.
Yeah.
So I had this job with Pat to become a radio astronomer, which also turns out to be very difficult. And to become a theorist, which also turns out to be very difficult. So at any rate, I really tried to avoid the cosmic background radiation. And then NASA said they wanted proposals for new satellites. Advisor, Pat Thaddeus, this project I did failed, but we should try it in outer space. So we did. And so I felt at the time the chances of being selected must be very small. And I didn't know how small they were, but it turned out 150 other groups also proposed at the same time. And so the odds were very small. But nevertheless, we got the
I think it's a very small chance as
So
well.
it's not all random. So I didn't know how important that would turn out to be. But I think what I always remind people about is something I learned from that failure was if you do not test something, it will not work. So we had been unable to test our balloon apparatus on the ground in Berkeley before we took it to Texas to launch it. And there were 3 reasons that it failed, 2 of which we might have found in Berkeley, and the 3rd which we never would have found. You just have to try because you can't test. But if you can test it, you learn a lot, and it's a whole lot cheaper than flying your project and having it not work at all. So anyway, there was a lot of discouragement, but on the other hand, I saw opportunity, I said yes. So as it sounds. So let's see if I can show you some charts. Computers are still acting up, but at least you're seeing the one that I mean to show you. I can't see it on my regular screen. Anyway, this is just a reminder for everyone that as you look at things far away, you look back in time, and I showed this in the public talk. a reminder that you look at things far away, you look back in time. So in order to look way far back in time, you have to look way far away. We do it by trigonometry and the standard candle method to find out how far we are looking. So we survey the universe. We measure the speeds of motions of distant things by the Doppler shift, which we see in the spectra. And fortunately, nature has given us sharp lines in the rainbows that we pick up, so we can do this. So just repeating a little bit of history here. Edwin Hubble is shown with the Mount Wilson telescope keeping a star on the crosshairs to get a time exposure. And let's use the laser pointer of the future. So here he is taking spectra. At least it would be if it were nighttime. And then we got our first picture of the expanding universe. And I don't know, I can't remember how much of the story I told yesterday, but I was not expecting this, and everybody thinks this is his greatest blunder. He had put in and he said so too, he had the equations that described this, but did not expect it, so we didn't find it. So you find a little bit what you're looking for. Anyway, it was from Einstein's general relativity, this was predictable. And so Friedman did it in 1922. He died in 1925 because Leningrad was a really terrible place to be after World War I. Lemaitre did it in 1927. He published it in an obscure journal, but not very many people read it. Then he predicted that this should happen. He had many of the same data points, but he did not draw a graph. And so since he did not draw a graph, the trend here was not obvious. And so, but he sort of knew it. Then lately there's been quite a flap about shouldn't he got more of the credit for making this prediction. And so it's very mysterious because this was later translated into English so everyone would see it. And he did the translation, but he left out some of the parts that would have given him credit. So he was not trying to get credit. He was an incredible guy. He invented the fast Fourier transform before it was invented later, and he didn't need it for very much. I guess nobody noticed, but anyway, Lemaitre was a brilliant man. There is a good reason to name a telescope for him sometime. Anyway, so now we know the story of the expanding universe. This is the COBE satellite, the one that followed my unsuccessful thesis experiment. So just to point out what it had, Earth below, sunshine on the side, and spinning around a vertical axis. By the way, we did keep the axis roughly vertical. So this is always pointed away from the Earth. The instruments here are always in the dark. The side, this is a special orbit. There are only one kind of orbit. It's called this polar sun synchronous orbit. So it turns out if the orbit plane of a satellite around the Earth is not exactly equatorial or polar, it will precess because the Earth is not round. But so there's a torque effectively on the orbit, and so choose the angle just right. In our case, a 97 degrees inclination, namely almost perpendicular to the equator. Then at that particular altitude, the orbit plane will rotate once a year as you orbit around the sun. So that means the sun is always shining on the side, the Earth is always below. So there's just this one place you can put an observatory like this near Earth and have the instruments always cold. It's not a good place to put a telescope because the direction you can point is always changing, looking straight up. Anyway, so that's why we put it there. And then, we know we got our spectrum experiment. The spectrum confirms that the Big Bang is correct, although we shouldn't call it the Big Bang. We got our map with the hot and cold spots. So this is just sort of a reminder of the basic cosmology that propels us to go after the universe. Now the map the COBE satellite got was not nearly as good as this one. This is from the WMAP project, and it's far more detailed, but in fact it agrees very precisely with the one that we got from COBE. So the hot and cold spots are, as far as anyone knows, random. But they are random in a curious way. They have a power spectrum. So there is a particular preferred size of these spots, approximately a degree in diameter, and that corresponds to the size of the universe when it became transparent. This map can be used to confirm the whole history of the expansion. And so there's a very long and complete theory about how to do this. Spots represent the early universe and the random fluctuations then. And we have basically a perturbation theory that can be used to calculate everything from this. If you start off with the assumption that the universe is populated by random spots, now you can say, now I think I know all the equations that govern how it becomes transparent. So the chemical equations for the atoms becoming neutral, for hydrogen and helium, both species. You think you know for neutrinos, dark matter, dark energy, and all these other things. And it's all small scale, small amplitude signals. And you can calculate everything you think you should see about the distribution of galaxies today. And the remarkable thing is you can get it to fit. So none of that was anticipated properly when we first conceived of this COBE mission back in 1974, because people were just barely beginning to be able to measure the distribution of galaxies, and there was no expectation that we would ever find these spots. So the theorists finally caught up with the experimenters just in time before we launched the COBE satellite. So there were predictions that were made just in time.
John, how much bigger than the angular resolution of the telescope or the instruments are the spots themselves, generally, on average?
Well, the spots on average are about a degree across. Angular resolution of a few arc minutes, you got quite a high resolution of the spots.
And that's what you got?
COBE did not. This one is close. And the Planck mission does have a few arc minutes angular resolution. So that means that you can actually get not only the characteristic size of the spots, but also the harmonics. I don't have the power spectrum to show you on the charts, but it shows one big bump for the size of the spots plus harmonics at 2, 3, 4, 5, 6, 7 times that particular spatial frequency. All of those little bumps and wiggles on that curve can be reproduced by this very simple, quote, simple theory of the early universe.
Yeah, this 1 degree characteristic angular dimension, what does that translate to in linear dimensions? If we don't think of units?
And the 400,000 light years across, which is the age of the universe when it became transparent.
Oh.
So what we're seeing is causally separate, disconnected chunks of the universe when suddenly they became transparent. So each one of these spots is a different piece of early universe that had never talked to anybody before. Time to do so. So that's the meaning of these spots. These are random pieces of early universe that never talked to each other before that. Now we see them because they're all talking to us. They've had time for us to receive the light from those spots. A curious kind of story to be telling, because you have to imagine that that this story that we're telling is things were expanding so quickly in the early universe that they did not have time to talk to each other. And then going back even before that, you have to imagine there was a time when they were sitting there long enough to talk to each other, so they all became almost the same temperature. So this whole map is uniform to a part in 10,000 or so. So how did that happen? Something had to be sitting there stationary before the expansion began so that it could come to an equilibrium. The whole visible part of the universe we now can see was supposedly occupied a volume about this large, which is not to say that's the whole thing. The whole universe might still be infinite even early on, probably was. So many mysteries in this plot, but curiously enough, they all seem to fit the theory extraordinarily well. And so when you analyze these spots, you say, you think you know the parameters of the early universe down to % accuracy. So it's because they're one heck of a lot of spots. You can get every bump and wiggle on the curve. So it requires dark matter, dark energy, between 3 and 4 kinds of neutrinos. The cosmic fluctuation starting off with a particular almost scale invariant spectrum. And So this is now called the standard model of cosmology. And if you got it right, it should match everything. So I showed this chart last night also just to remind people that what people think of when you hear about the Big Bang Theory is mostly incorrect. Because if you hear the Big Bang, you picture a firecracker, and this is exactly the opposite of what astronomers see. Firecracker at a particular point in space and time, we see an entire infinite universe expanding, and there's not a first moment, there's not an instant of creation, even despite the fact that a great many popular science explanations say they talk about the moment of creation that you can see. All we have in physics is process where something turns into something else. There is never a moment in our science where nothing turns into something. We have a vacuum, but that's not nothing. It's vacuum. So I ask everybody what are space and time, and nobody can tell me. So come back in another few centuries, maybe we'll know that. So how did we get here from there? Our story, which I like to remind people about, is that gravity makes things unstable. Gravity produces, so in astronomy we call it negative specific heat. So what do you have when something has negative specific heat? It wants to warm up or cool down all by itself. As an example, if you have a satellite orbiting the Earth and it feels air friction, it will lose energy by friction and it falls down closer to the Earth. But as it goes, as it falls closer to the Earth, its orbital speed actually increases as it gets closer to the center. Energy is going faster, so it spontaneously heats up. So people talk about the second law of thermodynamics and how it should lead to everything uniform at the same temperature. Gravity prevents that from happening, at least in practical sense. So this is the basic reason why we are here. Gravity makes things unstable, and everything about the universe is unstable. So do not think that simplicity is the natural state of affairs in nature. So anyway, it's unstable, so we can now make condensed objects. We've given a vast amount of study to how the gene's instability makes gravity pull things together. For it to actually happen, heat has to get out of the compressed gas cloud, so that governs the process of forming stars. And of course, we are here because of all this get started. Here's an example of what might have happened to the solar system. This is a simulation of the force of gravity operating on 4 giant planets and thousands of asteroids and comets. And so the simulation runs along sort of like clockwork, nothing much happens for hundreds and hundreds of millions of years. And then, as you watch it, something dramatic will happen. So that was just gravity operating on point objects. So it's a reminder that things are unstable. When Newton gave us the second law of gravity, and he said, I can now explain the laws of motions of the planets, philosophers were extremely upset. And the artists were very upset. They thought this has taken all the mystery out of life, because it was immediately recognized that you could have the idea of predestination, that if you knew where all the atoms and molecules were and the speeds where they were, you could predict where they would be forever. And so this is just a reminder that you can't, because even classical mechanics makes things chaotic and indeterminate. So whole philosophical subject about free will and quantum mechanics gets all confused because we imagine determinism applies when even it doesn't in classical mechanics. It's not deterministic, but you cannot calculate. There's no hope of calculating enough. So we are building new telescopes, and we've been planning on these for many years. Planning for these, by the way, started just about the same time that we started planning the James Webb Telescope. I remember going to a workshop we were having on the Webb Telescope, and just in the next town, the next week, was a workshop on these, on the ground. So people said, well, you obviously have to have something. So these are now 3 giant telescopes. They're all being constructed, and they will not be ready as soon as the Webb Telescope, but they will be ready while the Webb Telescope is operating. So we will then have the opportunity to see something with each kind and try it out on the other one. So we will have complementary observations, more or less the way that we have now between the Hubble and the Keck observatories, for instance, that we have on the ground. These obviously have more collecting area than anything we could possibly put into space. So if you see something with a Webb telescope, you will say, can I have time on one of these telescopes to follow it up with spectroscopy? And so you can get that will come through the atmosphere of the Earth. You can do much better with these than you can in space. So Hubble telescope is up and working. We have fixed it and improved it 5 times. And it is not scheduled to stop. To keep on going. It is operating in low Earth orbit, so several things could happen to it. One is it could stop working all by itself and would not be able to talk to it. One is it keeps on running forever and finally plunges to Earth, and that's bad because it might hit something. The mirror here is several tons of glass, and it will definitely come straight through the atmosphere and hit something. So we are not allowed to let that happen. So treaty says you must get rid of this in a safe way. Either aim it at the Pacific Ocean or push it up higher so it doesn't hurt anybody. I don't know that I'd mind so much getting hit by it, but if it landed on Moscow, some people would be very upset with us. So we cannot let that happen. So it's working. All of the instruments are going well. And so as far as we know, we'll keep on running until you all decide it's not worth it. And I think we're not likely to say that. So here's our ultra deep field of the Hubble. We pointed the telescope at this place with only one star and look at all the galaxies we found. It was a huge surprise for astronomers who had really tried to predict what this picture ought to look like, and we missed. What people expected was the galaxies took a long time to form. And what we found was they formed very quickly. And so when it means that they form very quickly, it means you cannot see them forming. The very first ones are beyond the range of the Hubble. They happen too far back in time, which means to see them you have to look very far away, which means they're very faint, and the wavelengths have been stretched out into the infrared, so the Hubble cannot pick them up. So this picture immediately told us, build us another telescope that's capable of picking up infrared light at longer wavelengths. And please build it as big as you can, because these things are very small and faint. So this was the hardest scientific requirement to meet, was to be able to extend this chart into greater distance and infrared. So that's why we are building the telescope that way that we are. And everything else was easier. Here is our location somewhere out here in a galaxy like ours. And eventually we would like to understand if there's any color in this chart. Putting blue stars that are new and fresh and bright and heavy and massive and burn brightly. And the pink areas are molecular clouds where stars are being born now. And the gray areas, the brown areas, are dust clouds in space between the stars where you cannot see at all. And of course that dust came from stars that exploded, like that one, Gram Nebula. So if I understand this right, there are actually 2 pictures superposed here. The blue is from X-rays, and the colors are from Hubble, taking pictures of different species, chemical elements that are in here. We know this is part of our history. Coming along to cosmology, people measured and expected that the universe would be slowing down because of gravitational attraction between all the galaxies. That's what my sketch illustrates. The Palomar Observatory was built with measuring this effect in mind. People said, well, we know the universe is going to be slowing down because of this gravity. We will build the Palomar. We will measure this slowing down. And they couldn't measure it, partly because it isn't there. It's also an extremely difficult technique. To do is to measure distances and speeds extremely accurately, and it's hard to measure the distance. So these folks are members of teams that got recognized for discovering the acceleration. 1998, discovery of the year, the accelerating universe. We actually call it accelerating. Some people would be interested in we didn't really see the acceleration. all we really see is that the distance from probability are standing angles are 20% fainter than they're supposed to be. So, however, we now say Einstein's constant that he introduced so that this universe could be static may actually be the one that governs the acceleration. I meant to tell you, by the way, that Einstein got to visit Hubble and see the information that he got, and he apparently was not convinced. Einstein was not convinced until 16 years until theorists explained to him that his own story had to be wrong. That the theoretical universe of Einstein was unstable. The Lemon constant that put in was not going to be able to make a stable solution. There was no stable solution. So anyway, we understand. So there we are. So now of course people want to know today, well, what are you going to do to extend this discovery? We had already confirmed this in many ways, including the details of the microwave map spots. But what are we going to do next? That's one of the huge pushes for astronomers, because this is the most troubling thing that we can see as astronomers is what is we really wanted this until it was found. These folks were not expecting that they would find the acceleration as well. So the Europeans are flying called Euclid, going up fairly soon. I don't remember the date. And the Americans are building another one, somewhat bigger, powerful, and operating at more and longer wavelengths, called the Wide Field Infrared Survey Telescope. We've just started ours. So they're hot topic to pursue the nature of this effect. The big question for us is this not a concept that fits the Einstein equation, or is there a physical thing about a substance, something that ought to be governed by an equation of motion, quantum field, or something else that produces this effect? So nobody knows. Observers have to do their part.
So John, when Einstein was told there's no stable solution, and did he just say, "Oh yeah, okay, I accept that," or was it that simple?
I think the other theorists did persuade him correctly, and I don't think he had any after he understood that his solution was unstable. It's not that hard to prove. He just hadn't done anything about it himself. So the Webb telescope is my main topic for today. So who's doing it? Goddard Space Telescope, where I work in Maryland, is leading the project. In collaboration with European and Canadian space agencies, Northrop Grumman Aerospace, and they have facilities all over the country. We chose the company by the way, TRW. Things changed. We have instruments coming from 4 different places. Our near-infrared cameras from Arizona, with their contract with Lockheed Martin. A spectrograph comes from Europe. It has 2 big pieces coming from NASA, detectors and microshutters, which I'll show you. We have a mid-infrared instrument, which comes from the European Consortium, and then confined guidance comes from Canada. They have contractors too. So all of these things are done by partnerships. There's not just one astronomer like me saying, "Please, let's do this." We have roughly 1,000 people currently working on the project. So when we get it ready to operate, we operated as a Hubble is from Baltimore. Telescope Science Building. So how many people have already been using the Hubble telescope or something? A few of you, but some. So the method for this one we almost need the same. The proposal. If you're chosen, then we'll give it for you, but we'll give it to you. And when eventually you will have to make the data public. So those are enormous. We want to cross the aperture here, and I'll show you how that fits into the project. There's a very cold sunshine down here. It's about 45 degrees Kelvin. So the instruments behind the telescope, rockets you can barely see, they operate between 40 Kelvin and the instrument is at 7 Kelvin, which requires its own refrigerator. So we'll show you that. So telescope is cold, so it doesn't glow, and it's going far from Earth. We've gone through about 1.5 million kilometers farther out in the sun. We're carrying fuel for years of scientific operations. According to the scope, we launched 2008, so it's over 2 years from today. At the launch date. And it takes about 6 months to get it ready for scientific operations. So starting in April of 2019, for 10 years means 2029. So your students still be able to use a telescope. So I'll talk about that. Oops, on back. Wrong direction. Okay, this is the sketch of the orbits. Here we are. There's the sun, the Earth, the Moon, not to scale. And there's the Lagrange point 2. We do not go to the Lagrange point 2. It happens to be right at the end of the Earth's umbra, so it's pretty dark over there. We actually go into an orbit that's several 100,000 kilometers in radius around the Lagrange point. For reasons. One is it's the cheapest orbit to get, so you can carry more payload up there. Another one is you must avoid the shadow of the Earth. We need sun power. We need solar electricity to run the observatory. So that governs all of the details about the trajectory of the rocket. So this is what the observatory looks like from various different perspectives. Here's the big primary mirror. There's a 5-layer metallized plastic sun shield. There's a warm box under here containing all of the spacecraft equipment, the electronics, the power supplies, the rocket engines, the fuel tanks, receivers, controllers of all sorts. It's all on this side of the observatory. So this side's warm, this side's cold. Here's the diagram showing the solar power coming in on the solar array. A side view showing you that the instrument box is behind the telescope. And it doesn't say anything about it here, but there's a electronics box down here which runs at room temperature, so that we can have a very short cable from there to there. And now this is an interesting hazard and problem for us, because now we have a hot body right here, and we've got to make sure the heat radiation all goes out that way, and none of it goes around to the business end of the telescope. Something else that's here, and it's labeled here, although you can't really see it, is called the momentum trim tab. So an interesting challenge for us is the fact that the sunshine pushes on the observatory. And we don't care much if it doesn't try to tilt the telescope over, but it does. So if the center of pressure of the sunshine, solar radiation pressure, is not over the center of mass, it tries to turn over the telescope. So this is a little flap where we try to adjust the center of pressure to match what we think it needs to be. Take a guess as to how big is the force of the sunshine. It's about 1 millinewton, which is like the weight of a fly. It doesn't take much if it adds up over all day long. And if you didn't do something about it, the telescope would tumble over in about a day. So anyway, that's the sketch of the observatory. This is a sketch of the light coming in from the sky and bouncing off the big primary mirror, which you can see is made out of 18 hexagons. And so it's almost a Cassegrain telescope. That's the part that you see. A big parabolic mirror, almost a big convex hyperbolic mirror here. There's a entrance aperture for the instrument package. Behind here, where you don't see it, there's a third mirror, which makes this something called a 3-mirror anastigmat telescope, which means it gets a much better image over a much larger field of view than the 2-mirror telescope will do. And the upshot is we can get a really good image. But we will have to adjust all of these mirrors to the right place. These 18 mirrors do not start off in the right place. They're a launched configuration, so they're protected. And then we let the locks loose, and then we have to move all of them into place. So that's pretty tricky. Another thing to point out is that they're made out of beryllium. And so why would you use beryllium? Why don't you use glass? Well, number one, beryllium is a whole lot lighter weight than glass in terms of density. And number two, it doesn't distort when you pull it down. It still shrinks, it does not warp. And so we had a giant competition. We had 12 different contracts with companies that said, we can build you one of these. And only one of them succeeded. So we have beryllium. It means that it's pretty hard to do. Beryllium powder is really bad for you. If any of it gets into your lungs, it'll never come out, and you can become hyperallergic, and you can die. So the machining of this beryllium is done in a sealed box with negative air pressure inside, so every single particle of beryllium that comes off the machine shop is captured and sent back to the factory to be rebuilt into the next thing. So the other thing is we have to polish it up at room temperature so that it will be the right shape when it is cold. So we call it cryo-polishing, which of course you cannot do literally. What you do is you polish it at room temperature, cool down the mirror to the low temperature that it will have. You measure what is shape, warm it back up, and then you polish in the inverse of that error. So the next time you cool it down, it's correct. Do that and it works. So that's what it takes. So these mirrors are extraordinarily accurate. The RMS error is about 25 nanometers on a scale this big. So if you were to scale up the mirror to the size of the continental United States, the error is about that much. Very small. So it's an astonishing accomplishment for the engineering teams that can do this. Here is a picture of our clean room at Goddard, where we were putting the mirrors together. So here are people out on what we call diving boards, hanging over the mirror to do what they had to do. Because for a while, for instance, we had dust covers, these black hexagons covering gold ones, to keep the dust off. You might say, well, why do you need dust covers? Who cares that much about the dust? And the answer is, of course, you cannot wash a telescope after you get it dusty. So try to keep it clean. So the entire wall of this room is air filters. And so it's still hard to keep it clean enough. Of course, where does the dust come from? Us. Dandruff and things from your lungs. So do not smoke.
Don, I know you tilt the individual segments to get it all phased, but do you actually in real time alter the shape of the individual segments?
Yeah, I didn't mention that, but each one also has one radius of curvature adjuster for each of those 18 segments.
Even you fly, you still do the adjustment?
Yeah, we've adjusted after flight, after launch.
Oh, right.
Yeah. I think, okay, here's another picture of the mirror. It's just beautiful. Very little gold, by the way. The whole amount of gold is fit in a golf ball. Probably one of our smallest expenditures of cash to get that amount of gold. This is a drawing showing, or a graph showing how good is the image. So astronomers want to know how sharp is my image. So our specification says it's called diffraction limited at 2 microns wavelength, which is to say it's almost perfect. Perfect enough at that wavelength. And so these are all calculations because we haven't got the telescope in space yet. But we calculate from the properties of all the mirrors that it'll be fine. And that even at 1 micron wavelength, the image will be very, very sharp. A bit sharper even than the Hubble image is. So here is how we know that this can be done. We made a scale model of the observatory telescope, small segments, and we learned how to set it up and adjust it. So the short version is if you take a picture of a star when you first get there, and you should see 18 out of focus segment, and then you move each segment a little bit so you can identify which segment goes with which image, and now you know how to begin. Eventually you have to combine all of these images together, and the last step, the final step, is when they're almost about right, we do what we did with the Hubble. We take pictures in focus and out of focus. And the electric field of a point source image is analytic function in 3 dimensions, which means that phase and amplitude are related. In principle, if I take enough pictures, I can send it to the computer guys, and they will say, turn the screws just so, and it'll be in focus next time. So we tried that, and so that's what we did here, and now we know we can do it. This is how we get our equipment around the country. Here's a truck with a special carrier. And there's the C-5 aircraft. So sometime after midnight, when we're done at Goddard, we will put our telescope all folded up into that carrier, drive it into the airplane, and fly it to Texas. And then when we get to Texas, we will put it in your big vacuum tank there. This is the same one that was used for the Apollo astronauts to practice going down the ladder of the spaceship and stepping out onto the surface of the moon, placed on the historic register. But we filled out the forms, so we were allowed to put a cooling system inside. So the inside of this tank will now get down to the necessary very, very low temperature. The telescope can operate at the flight temperature that it will have. So here's the telescope at the bottom. It goes in on rails. Looking up at equipment tested up here at the center of curvature. So we have computer-generated hologram that makes this parabolic mirror look like a sphere to the test equipment. So now we can verify that this thing has the right shape as a collective system. It's not quite right, of course, because gravity is operating on it and it's distorting all of the pieces, but we know what that's supposed to do. So we have various ways to verify that this thing will focus as it should in outer space. This tank is gigantic. It's twice as big as the one we have at Goddard. And as far as I know, it's the only place we could have done this work. So what are the instruments that we have that you might want to have your students use or use yourself? These are the cameras and spectrometers. So we go all the way from 0.6 microns wavelength, which here would be about that, reddish, all the way out to 28 microns wavelength, which is quite long. And a snake could sense it, but I can't. We cover the whole wavelength range, so we did not know in advance what experiment we wanted to do. So we said we better carry equipment for everything. So we've got several flavors of detectors, wavelength range. We have cameras, not so very wide field, but 2.2 by 4.4 arc minute square up here, a rectangle, and this one picks up a 3 by 3 arc minute square into little pieces. I can open up 100 shutters and let in your 100 different galaxies that you like into the spectrometer. I'll show you a sketch of how that works. This one has mid-infrared capability from 5 to about 28 microns, which is of course set by the detector technology. This one, and this one all, by the way, have coronagraphs. So a coronagraph is the thing you use to observe a faint object next to a bright one. So you basically put up your thumb and stop the bright star's image from getting into the equipment so you can see something faint like a planet orbiting around a star. So whatever you want to do, we hope we can provide it for you. Okay. This is the sort of trickiest instrument of all. This is called the near-infrared spectrometer. Sketch of how it works. Light comes in from the sky, from the telescope. We focus it, pass it through a filter wheel to choose the band that we want to work on. We focus the sky on an image of little shutters. We have 250,000 little shutters that can be opened and closed individually by command from the ground. So then the galaxies you care about, we let that in, and the galaxies you don't want to hear or see, rather, we block their light. So then this goes into a dispersive spectrometer, gratings and prisms and so forth. Eventually, what you get is an image that looks like this with a whole lot of spectra arrayed across your detector. So you get this back on the ground and you can figure out 100 galaxies. So you have the choices, spectral resolution. We didn't go to higher spectral resolution because people said, well, you could do that from the ground. So no need to try to do that in space. We even have on this one that thing called an image slicer, an integral field unit, which means I can take a small box of sky that's the 3 by 3 arc second square and divide it into little strips and get the spectrum of every piece of sky in that little box. How to anticipate the science that people will want to do. So how sensitive is it? Well, it's extremely sensitive. The sort of thing to remember is if you had a square centimeter of bumblebee at a distance of the moon, we would be able to measure it. Time exposure required, but sensitivity to see nanojansky levels of objects. Nanojansky is about 31st magnitude in the NAB magnitude scale. So something we're not used to thinking about. Nobody can see these yet, but we should be able to see them. On the other hand of things, people want to look at very bright objects, like nearby stars that might have planets, or our own planets are really bright. So we have developed a lot of ways to read out the detectors especially fast, so that we can get them able to observe all objects that we can. So everything from Mars outwards we'll be able to see. This is where we can look, by the way. It's a sketch indicating that we can look within 85 degrees of the sun, and between 85 and 135 degrees from the sun. Cannot look in the anti-sun direction because then the back of the telescope would face the sun. So we can look at roughly a third or a little more than a third of the sky on any particular day. As we wait for the observatory to orbit around the sun, it takes about 6 months to cover the whole sky. Here's on my scary movie. It looks simple.
Not really.
Not really. Yes. So it's complicated, very complicated. There are hundreds of things that have to operate properly to make this work. Because not only do the things that you see happening have to work, but there have to be locks to hold everything down during the launch, because this is all fragile. The mirrors are locked down for launch, this locked down for launch, everything is locked to protect it. And all of those locks have to loosen up before you can unfold anything. So you might say, well, how are you going to make sure this works? Well, we have several things. Number one, design it so that everything has more than one way to make it work. If there's a motor, you have two sets of windings in the motor, and you have two completely separate sets of electronics. So if one fails, the other one might work. If it's so two of everything we possibly can. We get committees of professional grouchy people to come and tell us when we're making a mistake. And of course they do. And so when we first designed this sun shield, which is the hardest and most unfamiliar part, they said that will not work. And so it took us 4 tries before we could get something where we said that probably should work. Then after you get to where you think it should work, then you have to rehearse it and practice. So I don't have a movie for you of them actually practicing, but they fold up the sun shield, and then they pull it out in a giant laboratory in California, and they practice until they see everything that might possibly not be quite right. So pretty beautiful, but also a little scary.
Were you able to only do subsystem shake and bake stuff, or were you able to do it as a together?
Well, I didn't talk about that, but yes, we do shake everything at each subsystem level, and then after it's all put together, we'll get a final shake
Of the whole
the whole thing in California.
That'd be interesting.
So shaking means several G's of acceleration in various directions in a random fashion. And we also have a sinusoidal sweep. We put in a sine wave and see what happens, which is actually quite dangerous because there are things with mechanical resonances that just want to amplify the vibration. So there are parts of this observatory that are expected to have 25 to 50 G's of acceleration because of the mechanical amplification of the vibrations that are applied by the rocket. So have to be really tough stuff because nobody's smart enough to say, yeah, that'll work. So coming back to science a little bit, my favorite movie of all time. This is a simulation in a supercomputer of a volume of about 100 megaparsecs of current day universe, expanding, although they've zoomed out so you don't see the expansion in the simulation. And what we see is very quickly the dark matter of the universe nucleates the formation of galaxies. And then ordinary matter starts to fall into the dark matter regions. And you can see that what started out as pretty random concentrations of material ends up now in strings and sheets and filaments of material. Look, now here we're sort of looking edge onto a sheet of material. And this is, it's observed in space, but it was really hard for physicists to think about it. We don't have good mathematics for simply describing a process like that. Maybe we do now, but when it was first observed in space, and we saw this stringy structure of galaxy clusters, big surprise. You cannot describe it by spherical anything.
Statistical equations are you solving to do this simulation?
So you start off with a random distribution of matter, including the dark matter, the ordinary matter, and you put in the equations of motion, kinetic equations, gravity, put in the equations of chemistry that govern the conversion from neutral gas back into ionized gas when the ultraviolet shows up. Some magnetohydrodynamics required because they're magnetic fields. Some things are a little too complicated to do accurately. So anyway, they put in as much as they can. And they start with about several billion mass particles, point particles representing the motions of vast amounts of material. So then you follow them all, and a variety of different computer codes can be done to do this. They do generically agree that this is the right sort of phenomena to expect. But it's clearly very difficult and expensive to do. This was the first simulation where people said, well, yeah, we think this is about right. So it's a few years old now. You can see some pretty famous names here of people doing this work. There are probably some more accurate ones that have been done now, but this, I think, is still the best movie that I've seen. So clearly we need to go from a movie like that, which shows a piece of rotating universe in front of your face, to say, well, if I took a picture with a telescope, what would I see? Because it's a completely different thing. You have to sort of imagine taking pieces of the universe at all times, from the beginning until now, and putting them all stacked up in front of each other. And then we take the picture, and then we have to undo the scramble. Then, in that case, the movie might have been right. So we're not there yet. But taking the picture with the Webb telescope is like the next step. Figure out if it's true. So Einstein gave us a prediction that this should happen. There are gravitational lenses in space. This is a cluster of thousands and thousands of galaxies, of which you can see the few of them here in the yellow. And there are many hundreds of these gravitational lenses that have been discovered, where you see in this case, a very magnified one, but there are lots of other ones here that are harder to notice. A lot of things which are sort of oriented particular ways, so you can tell the gravitational field has distorted the image. So we're already getting at this with the Hubble Space Telescope. And hundreds of them have been seen. Looking closer to home, one of our prettiest pictures, the Eagle Nebula, also called the Pillars of Creation. Stars are being born in here, and here's one you can just see, it's the new one. So I'll show you what happens if you go to a longer wavelength. You can see through the dust clouds. So I got asked today, well, how can you see through the dust? What's special? So the interesting thing is that if the wavelength of light is comparable to the size of a dust grain, it's like geometrical optics, and the dust grain will bounce the light off in some other direction, and it's a scattering of the light out of your line of sight. So you cannot see through the dust cloud. If the wavelength of light is long compared to the size of the dust grain, the wave can just sort of go around the grain and go on. So that's a small amount of it has been stopped, but most of it goes through. So that's the phenomenon that we're seeing here. The waves that we're using here are longer in size than the size of the dust grain. This is all calculable if you think you know what the dust grain is like. But of course, we don't really know. The subject of this dust is really complicated. So we now are able to see inside the cloud. And here's another example. This is a picture of a star taken with the Hubble. It's a remarkably complex cloud. You can see material flying this way and that. Dusty regions blocking your line of sight. There's just a little hint of a jet of material coming out here, but something violent is happening inside there. Here's what Hubble gets, taking a picture of the same spot. The dust is cleared up even at the infrared wavelengths that Hubble can do. So now you see this star inside with 2 jets of material coming out. And so now you can see. So we're going to do more of this. This dust will become more and more transparent. We'll be able to see into even deeper, dustier places, and eventually hope to understand this process where stars form with jets coming out. It's a pretty common process, almost universal, that new stars always have jets surrounded or combined with a disk of material orbiting around them. This is really tricky. Look, the jets do not seem to be coming right straight out of the star. So how is that? Well, lots to be learned. So we expect many, many observers to say, please look at my object. We're going to learn everything about star formation. If we know where it's happening, the tricky thing is to know how to interpret what you see. This is one of my classic movies of a planet going in front of a star. Blocks some starlight. This is what the Kepler Observatory had done so well, and others will do some more. The TESS Observatory will fly soon and will give us a catalog of planets going around nearby stars that are transiting in front of them. And we'll have this catalog of everything bright that there is to track down. So when the planet goes behind the star, you can also see a blink if this planet was really bright. So in my next picture, I'm going to show you what a hypothetical spectrum would look like that you could get from a planet going in front of a star. So here is a pretty big planet going in front of a star. Similar to a star that's already been seen with a planet. So here's a spectrum dividing the spectrum of the star with the transiting object, but the star without. So where you see this is definitely not a straight line across. This is because of particular molecules in the atmosphere of that hypothetical planet. What's in that atmosphere? Now this is a big planet, it's not like Earth, but you can see the signal is actually quite large and not hard to find.
Is this the methane of something?
Sorry?
Is this methane?
This would be one of the JWST instruments for the near spec.
The methane of something.
Sorry?
The methane. Methane.
Oh, is that methane? Yeah, I think I've heard that. I just forgot to put it here. Yeah, I think methane. So you should expect methane on a giant planet. So what else is out there? We'll find out. Just to illustrate that this is not hard for a big planet. It's really hard for small planets. A planet like Earth is only 1% the area of Jupiter. Less than that, and of course our atmosphere is also very small by comparison. Here, this is a very large signal. So we'll be able to look at the solar system. I mentioned earlier that we can look at moving objects, everything from Mars outwards. We have the ability to track things that move up to 30 milliarc seconds per second of time, which is pretty fast, but not as fast as the fastest things move. So whatever your particular interesting target is, think about it. There should be a time during the observing program where we'll be able to look at it. We might be able to go faster, but we haven't proven that yet. So if, however, you have if you've got a killer asteroid coming straight at us, probably not look at it. So please don't arrange to have one. So basically, we send up an ephemeris to the camera that controls the guide star, and we can get back what we want, we hope. So how are you going to get time on the observatory? Well, just as you do for the Hubble telescope, you have to write as a proposal. So there are several teams of guaranteed time observers who did work on the hardware or other things for the observatory for a long, long time now, since we chose them in 2002. And so they get guaranteed some time. So they have to put in their plan soon, what their program is. And then we're going to also have, although I don't have it on the chart, a community process to choose some early release science. So think is the most interesting thing for all of us to have access to immediately. And then in addition to, after those are settled, then we will call for proposals in early 2018. So about a year from now, we'll be telling you what to write and how to write a proposal. So you send in your proposal, and we expect basically every astronomer in the entire world is going to write us a proposal. A lot of committee meetings. And so this is how it's divvied up. First 5 years, 80% of the time is for the general observers, 10% for the director to decide, and 10% for these guaranteed time observers. A particular favorite topic, write us a proposal. So if you need more information, there is lots and lots online. We've had several conferences about the Webb telescope science. There's a whole issue of Space Science Reviews devoted to us. A long time ago now, 10 years, but basically nothing's changed about the fundamental capabilities or the basic science. What you can add is, well, we know a lot more about planets now. We know a lot more of some things, but what Webb can do for you is basically the same as it was. And we've had quite a number of white papers that our science team has written. And if you Google JWST white papers, you'll find them. So various kinds of tutorials on things that we think you would care about. So, oops. That's separate and additional, but let's have some time for questions.
I have two questions. First one is which factor sets the lifetime of data activity? And so which factor sets the 5-year lifespan of data activity?
Oh, what sets the lifetime? Well, we only promise 5 years because it takes an awful lot of work to be able to promise the lifetime of anything. So of course we're not going to do a 5-year lifetime test on the ground before we launch. So we will design with the intention of lasting 5 years. We are filling up the fuel tank, and the fuel tank will cover 10 years of scientific operations. So you could say, well, why do you need fuel at all? And two purposes. The pressure of the sunshine that I mentioned tries to tumble over the telescope. You have to occasionally fire the jets to get rid of the accumulated angular momentum. It is unstable. Lagrange point 2 orbits are all unstable. So it's good and bad. It means you have to fire the jets every few weeks to keep the orbit close to what you want. It's good in the sense that there is no accumulation of space debris out there, because it will naturally go away anyway. No cloud of little dirt grains.
And no cryogens.
We have no cryogen to use up. We do have a refrigerator. I promised to show you more about it, and then I didn't. Anyway, we have the mid-infrared instrument, runs at 7 degrees Kelvin. It uses a helium expansion refrigerator to get that temperature. Compressor on the warm part of the spacecraft and expansion at the cold end in between.
The second one is what are we going to do with the very cute test bed?
With a test bed, I mean, the small telescope this big, it's actually not useful for anything except testing the algorithms.
Can we have it?
Good question. I don't think we have any plan for it. But if you're excited about it, somebody else probably is too. So
Oh, I don't know.
you shouldn't have mentioned it.
Okay.
Yeah, how stable is your ongoing funding? Do you have to rely upon annual appropriations?
Yes, everything in the federal government is done on an annual budget. So in principle, everything is totally unstable. For the last, since we had to replan our program because our budget was terribly insufficient, and so was the schedule. And so in 2011, we made a new plan, and Congress approved of the new plan, and they said, we'll send you money. And so at the committee level, they remember. And so we've kept our bargain, we've kept on the schedule that we promised, and they kept their bargain, and they sent the money as planned. And nobody took it on the way. Nobody swiped it on the way, which is, government really can work sometimes. Not easy to get, but it works.
How do you address the question that many of us get all the time, which is, why is the James Webb Space Telescope so important? And how important is the mission for the general public or public knowledge?
Okay, well, a couple of parts. Number one, there's this huge gap in knowledge about everything that shines in the infrared. So after the Hubble was launched, a committee wrote a report that said this is why we need a new telescope that does this. So there were questions ranging from what happened after the Big Bang, which is the first objects that formed, to how do the galaxies grow, how do the planetary systems evolve, how come the solar system can have life. All of these questions sound pretty exciting to astronomers and I think to the public, although not all of the public. So anyway, the committee wrote a report which still gives me goosebumps to read it because it's so beautifully written. So they did a really good job of explaining why it's cool. Here. And I think the public seems to appreciate that, at least the people that care about astronomy, they care deeply. So this is the next enormous step for us. It's the capability advances far beyond what Hubble can do, opens up a scientific territory Hubble could not touch, because Hubble is warm. Hubble glows at the infrared wavelengths that we can measure. So Hubble, nothing you could ever do with Hubble is going to do what we do. And similarly, nothing you can ever do on the ground is going to do what we can do. So I think we expect to find something really wonderful and exciting. I just can't tell you what it is. We didn't find it yet.
Okay. What's the size of the annual operating budget once the telescope?
After it's up, it's about $150 million a year. About a third of that goes directly to astronomers to that are taken for them, and to give to their students and graduate students and postdocs. The other 2/3 is mostly for the people that have to operate the observatory, receive your proposals, review them, actually figure out the details of, well, you want to look at this particular star, well, how long, exactly what commands do we send, and then process the data that come back through a gigantic pipeline, the calibration factors, and says, we guarantee this is accurate. That's the other 2/3 of the budget.
Okay, any other questions? Okay.
Is there a lifetime for the JWST?
Yeah, we're carrying fuel for 10 years of science operations. We don't have anything that's going to burn out. So we'll just have to stop when we're out of fuel.
But the question is like a speeder, once you're out of fuel, well, you can use
Oh, where do you
one
go after
television.
that?
Yeah,
After that, it's over.
it's over.
We have, as for the ground-based or lower altitude observatories, we do have to make sure it doesn't come back to hit us. But it's really quite hard for it to come back to hit us. You just have to shove it a little bit and then go into your planetary orbit.
And you can't use it for like snapshot imaging or something at all.
No, it's over.
It's over.
As soon as we're no longer able to manage the angular momentum, it'll tumble. And
That's what I said. It's a snapshot.
Yeah.
Take a very quick one.
Yeah.
Give it take. Okay.
What is the reason for only giving it 10 years of fuel?
That's the size of the tank we had. Lasts a lot longer, but I don't know that.
I was wondering if you could give an estimate on the percentage of observing proposals that will be accepted by JWST.
I know I definitely can't, but I know for the Hubble it's quite small.
Yeah, I was wondering if
10 or
it's
15% or something these days. So people write an awful lot of good proposals and we'll turn down most of them. So, if you're not selected, do not take it personally.
Okay.
Considering all the other marvelous things that go into this, it doesn't sound like it would be totally impossible to design a refueling mission. The thing just goes out there and it's like linear refueling for a bomber.
Yes, we actually know what that would take, but we're not planning to do it. It's hard enough to do what we're doing. We have decided to paint the pattern on the end of the observatory so a robot could go and know how to dock. And so we know in general what we'd have to do, but we're not planning on it. When we started off this, it was completely hopeless to even think about it. Now it's not hopeless because we are building big rockets that could go there. And if you wait long enough, an astronaut could go there. But
On the way to Mars,
we cannot plan anything like that yet.
It's certainly possible in the future. It's when you have to think about 20 years from now, almost 20 years from now. I mean, So everything changed.
Yes, I fully expect it. In fact, the Congress would like us to make our future observatories so that they can be serviced. They recognize, as we do, that it's an awful lot of things at risk if you can't go there and fix it if you make a mistake. So we've got a really hard job of making sure you don't have to do that. Future ones, they say, please figure out how to go service it if you must. So the WFIRST is our next big one, and they're working on that. Figuring out how to do that.
Questions? Okay, one more.
Do you have any thoughts about the idea of sending a future telescope out 50 billion miles and using the sun's gravity well as a huge objective lens?
I've heard of that. That is actually an interesting idea. Yes, that if you had a particular special object that was really, really important to you, because you can only do this for one object at a time. So I think it's too hard for us right now. We've got to do the easy ones like this one. 50 billion miles is a long trip. But it's true, you could do that in principle. So things that I used to think are impossible are not. My friend Phil Lubin has been working on how you can propel a few grams of spacecraft to this quarter of the speed of light and send it to Proxima Centauri. So if you can do one, you can send 1,000 of them. So maybe we will. They're going to try. Things that used to be impossible are not anymore.
Okay, well, it's one wonderful talk, and
And their cookies and.
next cookie is
Right here.
oh, right here. Okay. Cookie is right here.
Okay.
And the next time you speak again is wonderful talk.
Okay.
No, I just.